Just a reminder that where we are now is we're saying that if we have a base distribution that we're comfortable with, and we have a transformation T that we can apply, and we can apply T inverse, and we can work out the Jacobian of T inverse, or possibly T, then we're going to be able to do sampling, and we're going to be able to do density estimation. And what's coming up now is we're going to be talking about how do we make those T's, how do we fit those T's so that we have those good properties that we're interested in. Okay. Any questions before we dive in?
I guess, yeah, just sorry. It's kind of a follow-up to the last question, which was like, how frequent do we need to do this? The maths looks a bit more complicated than mean field or something like that. So in your experience, how often do you use perhaps a slightly more complicated, more flexible methodology than the other more simple variational methods that might have a worse distribution, but it's good enough?
Okay. So first off, I'm going to put a disclaimer here. I'm a methods researcher, so I can't say too much about how often I would apply the one approach to rather than the other approach. I would also argue that I think that this is a lot simpler than variational methods because you don't have to worry about the elbow, the approximating distribution, all those other things. It's initially complicated in terms of understanding the Jacobian and what's going on, but once you have it as a tool and you've got a class of these models, they're very easy to apply and fit. Okay. Right, no worries. Anything else? Okay, so we have said that we're going to need this Jacobian determinant. And we're going to need this Jacobian determinant not just in practice when someone gives us an observation and we want to know what is its density, but also we are going to need this Jacobian determinant to train our model because we're going to want to know what are the density estimates for our data observations in our training set. Okay, so we're going to want this determinant computation to be very efficiently computable. When X and Z are d-dimensional, capital D, then that Jacobian is telling us about the rate of change of each component of X with respect to each other component. So that means we get a D by D matrix. Okay? A D by D matrix to compute the determinant is typically order D cubed. And one of the starting points we said was we want to deal with high dimensional problems. So D can be big. Right. So order D cubed is not something we're going to want. We're going to need a way around that. Okay. So we're going to be looking at ways that we can design our transformations so that that determinant computation is more tractable than order D cubed. Okay. So if we say that that's a kind of an absolute requirement, then in some senses, for what we are talking about, not mathematically entirely, we can now finally define what a flow is. So a flow is a diffeomorphism, which I've already spoken about before, that function that's invertible and differentiable in both directions. Okay? We're going to require that it's parametric. So we specify the function by specifying parameters. Because that's how we're going to fit it. We're going to train those parameters. Okay. That transformation must have an efficiently computable inverse so that we can move between sampling and density estimation. And it must have an efficiently computable Jacobian determinant so that we can do density evaluation and we can do training. Okay, so we need all these little parts. Okay, so that's generally a flow, and a flow allows us to move from one distribution to another. A normalizing flow is a flow where one of the endpoints of the transformation is connected to a simple base distribution. Okay, so flows allow us to go from one distribution to another. Normalizing flows start or end with a simple base distribution. And so later we're going to chain flows together to make a more complicated normalizing flow. Okay. So flows are a class of transformations for which one can efficiently perform change of variables. All we're doing over and over here when we're doing density estimation is we're performing change of variables maybe a number of times if we compose a number of flows. Okay, and we need to do it efficiently. So, we have our usual situation where we assume we have independent, identically distributed data. Obviously, there are other exceptions and other situations, but let's just look at this. We're going to assume that each data point is just a vector, so we're not worrying about spatial arrangement and other more complicated aspects. We're just going to work with vectors for now. And our aim is we want to estimate the function t, which we're going to basically do by estimating the parameters of t, however we decide to parameterize it. And one natural approach is to say, if I assume I know what my base distribution is, if I plugged in a certain set of parameters, that would allow me to work out the density for each of my data points. Then I could multiply all those probabilities together, and that would give me the likelihood of my data under those parameters. Right? So, if we can work out the likelihood, then that points towards the direction of choose the parameters to optimize the likelihood. That's the maximum likelihood principle. Okay? Ideally, we want to be able to optimize these parameters from the likelihood with gradient descent. If we can't do it closed form, which we almost always can't. Okay, so we're going to be looking at optimizing the parameters t using maximum likelihood, typically with gradient descent. Okay. Now, yeah, we're just saying we want to maximize the likelihood of the data, but at a more fundamental level, what we're actually wanting to do is we want that the distribution of the transformation of the base distribution must match as well as possible the true distribution. So later on, we'll look at alternatives to maximum likelihood. We say, how else can we try and evaluate this relationship? Okay, but for now, we'll stick with maximum likelihood. Okay, there are some problems with maximum likelihood. One of them is overfitting. So you can, in certain situations, tune your parameters to make your data more and more and more and more likely without necessarily generalizing well to other data that you haven't seen. Okay. So one way of avoiding that is regularizing. Another way is to not use all transformations. So you constrain the space of transformations. If you only allowed linear transformations, you would be quite limited, right? So if you get reasonable likelihood in that situation, chances are it might be a good model. Okay. So if we don't want to look at all transformations, but only a subset of transformations, that in any case naturally points to the idea of parameterizing our transformation space. Because if we've got a parameterized class, then we probably have got a restricted class. So we try and build a flexible set of functions with a set of parameters that we can estimate, but that do not necessarily encapsulate all functions to try and mitigate overfitting. Okay. Fortunately, yeah, by the way, we also have some benefits that if we're going to train this with SGD and we use a neural network, then we typically get the benefits that neural networks, large neural networks have against overfitting as well. So that is a bit of a nice side benefit. Okay, now, just to recap this, I think this should be very well known to most of you. Parameter estimation for a Gaussian. Okay, so a Gaussian has got, for a higher dimensional Gaussian, you've got a mean vector and you've got a covariance matrix. And you want to estimate them, and you might want to use maximum likelihood. Now, this is a little example, and it's a little bit fiddly because actually the argument I'm making is circular, but let's look past that for now and say that if we had a Gaussian random variable x with mean mu and covariance matrix sigma, we can actually get that x by transforming a standard Gaussian distribution z by applying an affine transformation. Okay, so we've done that with diagonal covariance matrices in the work that Matthias presented before. This is just slightly more general, where we take the Cholesky decomposition of sigma, which you can think of as a little bit like the matrix square root. Okay, so I'm instead of saying, oh, I've got variances on the diagonal, and then I take the square root of each component there, I've got a more complicated covariance structure between my components. I can decompose that into LL transposed, where these are triangular, so that's very nice for us. But ultimately, we can find the best mu and sigma by optimizing the likelihood of X with closed form optimization. Once we have mu and sigma, we can sample general Gaussians by sampling Z and applying the transformation. That's a very, very simple flow. Okay. When we are doing that, if we wanted to do density estimation for the complicated distribution X in this situation, assuming we didn't have the general Gaussian density estimation formula, we could get the density by performing the inverse transformation using the density formula for the standard Gaussian, and then applying a suitable scaling factor that we get from the Jacobian determinant. And if you'll remember, in the general Gaussian formula, what you've got extra that you don't have in the standard Gaussian is the determinant of the covariance matrix sitting in the denominator. That is coming from the scaling that's happening over here. Okay, so this is literally just a flow. You're going from the simpler distribution, which is the standard Gaussian, to the more complicated distribution, which is the general Gaussian. And you can sample by using that affine transformation, and you can do density estimation by going back to the standard and using the base distribution and accounting for the change in density. Okay. And in this case, we can actually optimize this thing with closed form optimization, but in practice, we can't. Okay, we have more complicated distributions. We need other ways to optimize the likelihood. Gradient-based methods are nice if we can work out the gradients that we need. And nowadays, with automatic differentiation, it's usually fairly convenient to work out very many gradients. So that's a good situation. Downside of gradient descent-based methods is, as in general with multimodal problems, that the likelihood isn't typically convex. You can find local optima. I'm not going to delve into how we deal with that beyond saying we rely on the same sort of things that we do with neural networks, with restarts, new seeds, and hoping that neural networks just converge well to good local optima. Okay, so key thing here. The Jacobian that we're interested in looked like a complicated thing, but if you look at the terms that are in it, it's a bunch of partial derivatives. Automatic differentiation excels at working out partial derivatives. So we can leverage the automatic differentiation capability that is already in things like PyTorch and TensorFlow and so on to help us calculate the Jacobian with automatic differentiation. And then we can use the same tools to do stochastic gradient descent. Okay, so that is the roadmap of how we do this. Any questions at this point? Okay, now, so far I've only looked at one concrete example, and that was a linear transformation. Now, if you want more complicated transformations, we can take other classes of transformations that we dream up, but if we're going to use these neural network tools and automatic differentiation tools, then it seems natural to follow a similar approach of saying we make complex transformations by composing simple transformations, and we introduce nonlinearity along the way by including things like activation functions. Okay, so we're going to compose simple nonlinear transformations to make complicated nonlinear transformations. If each transformation along the way is invertible and differentiable, and their inverses are differentiable, then the composition is going to be differentiable. The inverse composition is going to be differentiable. Okay, so, and the composition is going to be invertible. Okay, so in other words, we can basically if we've got a class of basic functions, then their transitive closure, if you're familiar with that, is the space of transformations that you can work in. Okay, but effectively this means we can design one layer and then we can chain layers together to make more and more complicated, potentially, transformations that we are interested in. Okay, each component that we chain together is doing its own job of stretching or compressing the density, right? But if we think of the determinant of the composition, mathematically the determinant of a composition is the product of the determinants of the components. Okay, of the Jacobian. Sorry, I forgot the word Jacobian in there. And so we can learn to handle the determinant Jacobian, we learn to handle the Jacobian determinants for each component, and then we can automatically put them together by just multiplying them, or if we're working in the log space, which is what we will do, we'll be adding them. Okay, so everything will work nicely. We're using the chain rule to combine the Jacobians. That's the one that says that the Jacobian of f composed with g is the Jacobian of f multiplied by the Jacobian of g. Okay. Importantly, we need the components to be nonlinear. If we have only got linear components, if we compose the linear components, we stay with linear functions. So we get no benefit of getting more and more complicated transformations. Okay. If we do this right, each layer should add, the amount of computation should scale linearly with the number of layers. Okay, and so what we're going to later have is we're going to say, we want to add as many layers as we can handle computationally. We don't want to use layers unnecessarily because it slows things down and makes training hard, but we want the number of layers to be enough to be able to express the complicated distributions that we want. So there's going to be a bit of a trade-off of expressivity versus computation. Okay, now, just to make this a bit more concrete, T, remember, is what we apply to our base distribution to get the data. Okay, so X is equal to T of Z. Now, in this case, we're going to have a whole lot of intermediate values because we're chaining these functions together. So we're going to say Z is Z0, and then when we apply the first transformation, we get Z1. When we apply the second transformation to that, we get Z2, then we get Z3, and so on. And if we have capital K layers like this, the final output is going to correspond to observation. So that's going to be ZK. Okay, so that's what we've got here. We're applying T to the base distribution value Z0. We get T by composing K functions F1 to Fk. And this generates in turn Z1, Z2, Z3, Z4 up to Zk. And that Zk is supposed to correspond to the observation X. Okay, so X and Zk are the same thing here. Okay. Now that is going from the base distribution Z0 to the observation Zk, but likewise, because each of these functions is invertible, we can invert each step, start with the observation X or Zk, and work backwards. Apply Fk minus 1, Fk inverse to get Zk minus 1. Then apply Fk minus 1 inverse to get Zk minus 2. And so on and so forth until we finally apply F1 inverse to get Z0, which is from our base distribution. Okay. So we literally are just combining and composing these simple transformations. Each transformation on its own is a flow. When we attach Z0 with the base distribution, we get the normalizing flow. Okay. Now, we already said what the change of variable formula was for a single layer, if I go back a bit. Okay? I said the density for X is the density under the previous distribution Z of the inverse of X. And then I scale it with this determinant. Okay. Now, note here that if I write this in the log domain, I'm saying that the log density of X is the log density of Z plus the log absolute determinant of the Jacobian. Okay. So what I'm going to do is I'm going to do that. Yeah. There's a log density of X. there's the log of the base distribution. So remember here, Z0 is the inverse of under T of the X value, or ZK. And then I've got to add the log of the absolute value of the determinant of the Jacobian. Okay. And that log absolute value determinant Jacobian is equal to that negative sum over there. So why is that the case? Well, because the determinant of the Jacobian of the whole transformation T decomposes as the determinant of each component Fk, Fk minus 1, Fk minus 2, and so on. So I'm taking the determinant of the whole T becomes the product of the determinants of each of those components. And then that product, I think that is load shedding. Okay, maybe it's not load shedding, but it's a glitch in the matrix. Maybe the Jacobian matrix. Okay. So the absolute value of the determinant of T is going to be the product of the absolute values of the determinants of each component, and then the log is going to separate that product into a sum. And that's why we get the sum over here. And then why do we have a minus instead of a plus? Because I'm taking the determinant of the Jacobian of the FKs and not the FK inverse. And I briefly referred to that over here, where I said that you can work out the Jacobian of T inverse at X or the Jacobian of T at the inverse of X. So either you can say, at the destination, how much am I stretching things when I go to the source? Or at the source, how much am I stretching things when I go to the destination? And those two are going to be inverses of each other. Right? So I can work out with either one. And when I multiply by the one, it's the same as dividing by the other, and that corresponds to adding or subtracting appropriately in the log domain. Okay, so that gives us this change of variables formula. And this is what I was saying about once you kind of are there, you don't need to worry about a lot of the complicated math, as long as you can work out those absolute value determinant Jacobians for your transformation. Okay. Now, let's consider density estimation for some x. To apply the change of variables formula on the previous slide, we need to be able to invert each fk. Why? Because I need to know what zk is, I need to know what zk minus 1 is, zk minus 2, zk minus 3 to plug them in there. Okay. So to be able to train this thing, I absolutely need to be able to go backwards along each step. Okay. That means that if I'm going to use a certain kind of function here, I need to be able to apply the inverse. Okay. Now, if we used a linear transformation and we made sure it was full rank so that it was invertible, it might be expensive, but we can perform the inverse. So we know that full rank transformations is a legal set of transformations we could use here. But in general, we might not, if we've specified fk, know how to work out fk inverse. We might only have implicit access. We might know that it exists, but we might not know how to work it out exactly. Sometimes we can use numerical methods to invert the function. So like root finding methods, like Newton's method. Okay. So to make these systems work, we need, for density estimation, either to work with invertible transformations, things that are easily invertible. So we design them so that we can find the inverse. That's the one approach. But there's another approach, and that other approach is to design it so that we can work out the inverse, fk inverse, only. So then we know that fk exists, but we don't know how to work out fk. But we can work out fk inverse. If we can do that, we can use fk inverse to get the base distribution, the base value corresponding to an observation, and we can work out the log determinant Jacobian that we need, and so we can do density estimation. Quick question, just think about this. What can't we do if we go in that direction? Maybe if you're reading the slides, you already know. Okay, so the slides say we give up on sampling. Does anyone have an intuition for why we are giving up on sampling? What is the problem? We don't know F. How do we sample? We start at the base distribution, and then we have to apply all the layers of F. So if we don't know how to go back from F inverse to F, we can't apply F. So if we want to fit a flow so that we know P of X, but we're not interested in sampling from it, so we just want a probabilistic model that's not generative, we can use a more broad class of functions where we just know the inverse exists, but we don't actually know how to efficiently get them. Okay, so that's a helpful thing to know. Okay, so this slide just sort of illustrates the trade-off that we have between expressivity and ease of inversion. So the left column here are 4 different examples. Each one's a target density. So this is the true P of X, if you can think about it in that way. And on the right-hand side, we plot results from something called, or not we, they, plot results from NICE, nonlinear independent component estimation, which is an early flow model. And this flow is designed to be easily invertible. Okay, so the impact of that is that the ease of inversion limits the complexity of each transformation step, and that means that when you only use 2 or 8 Fs in your T, you're quite limited in terms of what your function can do, and you don't get a good fit. So you need lots of layers, like 32, before you start getting a reasonable fit to P of X. Okay. The section B here uses something called planar flows. Planar flows are more complicated. They can do more complicated transformations for each of the individual Fs. But they are not something that we can directly invert. We don't know how to invert them. Mathematically, we can prove that the inverse exists. Okay. In that situation, you can see that with only 2 or 8 layers, well, for some cases with only 2, but typically with 8 layers, we already have quite a good fit to the true P of X rather than 32. And that's because we have this extra modeling capacity, but at the cost, I cannot generate samples from this distribution in this situation. Okay. All right. Just as a side note here, if I'm only going to use FK inverse, then I will use a slightly modified formula here where I've got the determinant of FK inverse in there and a plus instead of a minus with FK, because that's the function I'm going to be using. Okay. Any questions at this point? Okay. So far, we sort of assumed maximum likelihood without really critically examining that point. And I'm going to go into that a little more now. Because maybe we can find a way that allows us to fit our model. Remember, we need to fit the model. To fit the model with maximum likelihood, we need to be able to work out T inverse. And if we want a rich class of flows, then we're not going to be able to sample. So the question is there a way to fit a rich class of flows that allows us to sample? Okay, and one way of doing that we're going to look at now is to bypass maximum likelihood. Okay. So to fit a flow with maximum likelihood, we need to repeatedly apply T inverse, which is the direction used for density estimation. If we only have density estimation tasks, we design the flow possibly with only T inverse efficient to evaluate. But if we want sampling, we either need to accept limited expressivity so that we can efficiently invert our flows, or a different way of training the model. Okay. our original aim before we got to maximum likelihood was saying we want it so that when we take our base distribution Z and we transform the distribution with T, the resulting distribution should be like the data distribution. Okay. We want one distribution to be like another distribution. Okay. How have we compared distributions so far earlier in this summer school? What tool have we used? KL divergence. Okay. We're working towards it, but yeah, we're looking at metrics or distances or divergence measures between distributions. That's what we want to know. How do we measure the difference between these distributions? So if we think of a specific t being parameterized by theta, then we get a density over x when we choose a specific theta. And we got the true distribution p star, and we want those two to be small. So one approach is to say, define a way of comparing our distributions, and then try to make that difference or divergence small. Okay, so there are two major ways that are used for measuring differences or divergences between distributions. The one class is called integral probability metrics. Okay, and that math looks quite scary. We're not actually going to use it, but just so that you got this context, what an integral probability metric is doing is it's saying that if I work out expectations under the one distribution and I work out expectations under the other distribution, I want the answers to be close. So if I've got a collection of possible functions that I work out expectations over, and I work out the biggest difference between the expectations for each of those, and that is small, then that's a good indication that the distributions are close to each other. Okay, so if you've ever looked at things like Wasserstein-Gans and so on, this stuff comes up quite a bit, and the idea there is that you have that this F class that you're looking at, this collection of functions, is a collection of not too complicated functions. So if you do functional analysis, like a unit ball, for example, of functions. So this is a more complicated way of doing things, but there's a lot of interesting work happening now in terms of saying, under what conditions can we say how well our functions that we fit when we optimize this, how well do they generalize? Okay. The other major class is a class of this divergences called F divergences, which generalize KL divergences. So you see we're working out the expectation under the one distribution of some F of the ratio. So this ratio is going to be, when these distributions are the same, is going to be 1, right? We assume that this F, a requirement is that F of 1 is 0. So if these distributions are the same, then the thing inside the expectation is going to be 0 everywhere, and so this density is going to be 0. Okay, and one can show with Jensen's inequality over here, because we assume that F is convex, that 0 is going to be the minimum. So in this situation, what we'd like to do is we'd like to drive this df down to 0, and when df is close to 0, it means that those distributions are similar. Okay, so these are two major approaches we use for comparing our distributions. When we specify f of r equal to r log r, we get the KL divergence out. So that's a very specific example of an F divergence. Okay, and this divergence is very popular as this difference of expected difference of logs, because it's got a nice interpretation from information theory. Okay, so in information theory, we can talk about the entropy of a distribution, and that's telling us for that if we wanted to design the best code we possibly could for transmitting information that's been generated by that distribution, how many bits do we need per observation to encode that data? Okay, that is what entropy is. That's the best we could possibly do. Okay, in this case, we have got that the one term, the expected value of log px, is the actual entropy, and the other term is something called the cross entropy, which is saying that let's say we thought the data was being generated by a distribution Q, and we optimized the code for that, but the data was actually being generated by P. How many bits per observation am I going to typically need? And I'm going to need a little bit more than I would have needed if I'd optimized for P directly. Okay, and that excess that you pay for using the wrong distribution is the relative entropy or the KL divergence. If that difference is 0, it means you were coding with the right distribution. Okay, so that's a good fit. Okay, so all of this motivates that we want to use the KL divergence in some sense, or the KL divergence seems like a good way of saying whether two distributions are similar or not, and maybe we can optimize that. If we can optimize that instead of maximum likelihood, then maybe we can do sampling efficiently as well. Okay, without sacrificing expressivity. Okay, Matthias has already spoken about all the important stuff on here. Okay, we want to optimize KL divergence. But the first thing you do when you do KL divergence is people say, oh, but actually maximum likelihood is just optimizing KL divergence. Okay, and that is true. Well, you're actually optimizing, if you optimize the forward KL divergence and you use a Monte Carlo approximation, then you get maximum likelihood out as a surrogate objective that you want to optimize the forward KL divergence. Okay. But this points in the direction that the forward KL divergence is not going to be what we need because maximum likelihood doesn't work for us. So what do we try? When we did variational inference, we didn't do KL divergence. We didn't use the forward KL divergence because we didn't have the correct posterior. So we used the reverse KL divergence where we took the expectation with respect to the variational distribution because that was something we could control. So we do exactly the same thing here. We optimize the reverse KL divergence. So we just swap the arguments of the KL divergence, which means that the expectation we take now is with respect to the distribution that our normalizing flow is generating. It's not with respect to the true distribution. Okay, now, one good thing about this is we don't need to be concerned about overfitting anymore because we don't have our data sets in here anymore. But then the question is, how are we training this? Okay. Well, remember the idea was to say that if I sample from my true data, from my base distribution, and I then generate data, if I transform my base distribution, I want it to look like the true distribution. Okay, but how do I know what my true distribution looks like? The forward KL divergence used the data set because that was what told us what the data distribution looked like. Yeah. If we don't have a data set, we don't know what the data distribution looks like. So yeah, we are going to apply this to situations where we know what P star should look like. Okay, so there are two places that that's going to show up. The one is going to be variational inference. So we might have a posterior that's unnormalized. So that's close enough. We're going to be able to use it for that. The other one is we've already fitted, for example, with the normalizing flow, but perhaps with something else, a density estimation model to something. So I can estimate densities, but I can't sample. Then I can use the densities that get generated by that model as a P star and fit a sampling model to that. So that I can have a separate sampling model from my density estimation. Okay. So this is going to be helpful for sampling more generally and variational inference. Okay. Note that this expectation over here needs us to be able to sample from this, which isn't a problem because I sample from Z and apply the transformation. I've got to be able to work out the log of this, which is fine. And I've got to be able to work out the log of this base distribution. When I've got a density estimator, that's fine. When I'm doing variational inference, I don't know P star. Exactly. But I know it up to the normalizing constant because it's the prior times the likelihood without the normalizing constant. And I can take out the normalizing constant and I can ignore it because it doesn't depend on theta. Okay. And so I can optimize this with only access to the unnormalized density. Okay. Okay. So this is quite a long-winded detour, I'm afraid. But if we are willing to forego density estimation, so instead of sacrificing sampling on the altar of efficiency, we're going to sacrifice density estimation. So we're not going to do something that focuses on density estimation. We're going to focus on building something that can sample when we know what P star of X looks like, up to a constant factor. Okay? We can then avoid inverting the flow at all, which allow us to use expressive transformations for sampling models. Earlier, we could do expressive transformations for density estimation. If we want expressive transformations for sampling, i.e. not easily invertible ones, the avenue we follow is using the reverse KL divergence. Okay. Note that when we do this, we can optimize the reverse KL because we're getting our MC samples from the flow. And in other words, when we generate them, we are generating the Z. We know what the inverse is for that point because we take it forward. And that is what allows us to actually fit this model. Okay. So to summarize, in order to fit with the forward KL divergence, we need to be able to compute the density, the base density, and compute T inverse. We don't necessarily need to be able to sample from the base distribution or compute T. Okay. To fit the model with the reverse KL divergence, we need to be able to sample from PZ and compute T, but we don't necessarily need to be able to compute T inverse or compute the base density. Now, typically, you would be able to compute the base density, but it's not required. When we use the reverse KL divergence, we're going to get sampling efficiently, but perhaps not density estimation. Okay? When we use forward KL, we're going to get density estimation efficiently, but perhaps not sampling, depending on the expressivity we use. Forward KL needs a training set of data so that we can fit maximum likelihood. Reverse KL doesn't need that because we can generate values from the base distribution and use the access to the unnormalized density function that we have. Okay, so that is the sort of things that guide your decision on which training objective you want to use when you're fitting your flow. If you're going to use something that is easily invertible out of the box, and you don't necessarily know the density, the default thing will be just fit it with maximum likelihood. But if you want to build a sampling model that's very expressive, or you want to use it for variational inference, then you're going to be using the reverse KL. Questions at this point? Okay. Right. So that was the next major piece of the puzzle. We now have a situation where we kind of know how we should be doing density estimation and sampling, and that which ones we can do more efficiently depend on the expressivity of the functions, how easy they are to invert, and now my brain is switched off, I'm afraid. Okay, so let me reboot. We know that we can use T inverse in the Jacobian to use these normalizing flows for sampling and density estimation. And to fit them, we can either use maximum likelihood, which you can think of as forward KL, or you can use the reverse KL, depending on the aim that you have, sampling versus density estimation, and the expressivity that you're interested in. for your distribution. Okay, now, much of the research from that point is about trying to find good types of flows. Okay, so what kind of functions can we use for T or for each of the component Fs? We're basically going to focus, every flow that I talk about here is typically going to be one F that we compose into a larger thing by composing them. Okay, so this is just from a survey paper no longer last year, 2021. So they talk about autoregressive flows, linear flows, residual flows, and we'll talk a little bit about each of these classes to convey some of the key ideas we have about how do we make these flows invertible, how do we make the computation of the Jacobian determinant efficient, and open research here is saying, can we add new classes of flows? Can we add new types or subtypes of these different flows in such a way that we can still compute T or T inverse efficiently, that we can compute the Jacobian that we need efficiently? Okay, so the first one we're going to look at autoregressive flows, and we're going to look a little bit at contractive residual flows and flows based on the matrix determinant lemma. So I'm afraid here lies dragons in terms of there's some linear algebra and that kind of stuff coming up, but I have faith in you all. Okay, autoregressive flows transform each dimension in turn. So this is basically saying that the transformation I apply will only use Z1 to compute X1. Then it will use Z1 and Z2 to compute X2. Then it will use Z1, Z2, and Z3 to compute X3, and so on. Now, this is rich enough to capture all transformations. So nominally, you've got the expressivity you need. But if you do it in this way, a nice side effect is that because, for example, Z1 doesn't change as X3 changes, the partial derivative of Z1 with respect to X3 is going to be 0. And if you generalize that, you'll see that half of the Jacobian is 0, making the matrix triangular, the Jacobian matrix triangular, and the determinant of a triangular matrix is the product of its diagonal entries. And so instead of having a cubic determinant computation, we now just need to be able to work out those diagonal entries and take their product. Or if we're working in the log space, add their logs. Okay, so we move from cubic to linear. It's a wonderful time to be alive. Okay, so this is what our autoregressive modeling situation looks like. Each XD is a transformation of the corresponding ZD, but the way we transform it is going to depend on only the earlier Zs that came before it. Okay, this transformation tau here is going to be called the transformer. It says how we transform ZD to get XD, and the transformation is parameterized by CD, which depends on the previous values. And because this provides conditioning information, CD is called the conditioner. So autoregressive flows have transformers and conditioners. As you'll see here, there are different transformer types and different conditioner types. Okay. I've already mentioned that as a result, the Jacobian is triangular. But another thing is we're going to have to apply these functions quite often. So a cool thing to note about this is that if I've got these CDs, and each of them is a little network that takes in certain values, yeah? Then if I'm given all the Zs together as a vector, I can do the forward pass for each CD in parallel and work out all the conditioners at the same time, and then apply all the transformers at the same time to each ZD with the conditioner values, which means I can transform all the components of Z, of my base value Z, to the corresponding X's in parallel. So the transformation is not linear in the dimensionality. Okay? It's a single feed-forward pass over a number of networks in parallel. Okay. Another cool thing is that this transformation tau here while that has to be invertible, it actually turns out that this conditioner doesn't have to be invertible. I can make that a non-invertible function, but the result is that I can still invert the entire transformation tau, which is very nifty. Why? Because we can invert the flow in increasing order of D. So just to illustrate this, by the way, very important, the transformer I'm talking about here is not the normal transformer model in neural networks. Okay, so it's a different thing. Okay, so just to illustrate this, computing and inverting an autoregressive flow, let's say I want to transform the Z primes at the top here, are actually the X's, okay, the observations. So this is going from one F, it's applying one transformation F in a sequence, right? So this is one step. To transform the Zi to its corresponding X, I have to apply tau, okay? To apply tau, I need the value of the conditioning variables. I need to know what Ci is. How do I get Ci? I plug in the earlier Zs, run them through Ci to get the parameters. I use them together with tau to apply to Zi to get Zi prime. I can do this for each Zi in parallel by doing the feed-forward pass through each of these Ci in parallel. Okay, now let's say I wanted to invert that. Now this flow is very nice in terms of expressivity. How do I invert this? Well, if I wanted to invert this particular X, which is now Z prime here, I would need to apply the inverse of tau. This is why tau needs to be invertible. Okay? So I need to go back, but to invert this, I need to know what the parameters were that I got from the conditioner. I don't know, to know those, I need to be able to plug in the earlier Zs. Importantly, the earlier Zs are not the earlier Xs. Okay? So I can't directly work that out. I first need to work out all the earlier Zs. Once I've got them, I don't need Ci to be invertible because I can plug them into Ci and get the Hi, work out the inverse, and go back to Zi. Okay, so I can do that for each component in turn, and I can start with Z1 or with X1, going back to Z1, because it doesn't have anything to condition on. Once I've got Z1, I can invert X2 to get Z2 using Z1, and so on. But the important point is I have to do each component here in sequence. So inverting this is linear in the dimension. Okay, it's at least D passes through this network in sequence. It's slow, but it can be done. Okay, and early flows did do it. Okay, so this gives us slow inversion, but a nice flexible model. Okay, note here that we can now apply the T, or at least a component F. We can apply F inverse. We haven't said anything about the Jacobian determinant yet. And the reason is because the Jacobian determinant is going to depend on what tau is doing. Right. So that what tau is going to do depends on which transformer type we use. So let's just keep a very simple model, the affine transformer. Affine transformations do shifts and scales. Shifts aren't going to change the volume in any way. So the scaling component is going to be what's going to really drive the Jacobian. Okay. Now, note that while we are applying linear transformations to each component, we're applying different ones that depend on other components in different places. So this is not a simple linear transformation on the entire input. So this is a nonlinear transformation, and it's a rich transformation, but the transformer is an affine transformer, and that makes computing the Jacobian determinant convenient. Okay, so we want to shift, add some m, and we want to multiply by some factor. Okay. We don't want to multiply by 0 because then we can't invert. Then things aren't full rank. So we want to multiply by something that isn't 0. And so we could try to stay away from 0, but a more convenient thing is to force the value to be positive and then output the log. Okay. So the transformation we use is m plus z times e to the s. So in this case, the things we condition on are s and m, the scaling and the mean factors. And the idea is that s and m get output by the conditioner. So the previous components tell me how much I must shift and scale this component in order. Okay, now this tau is very easily invertible. If I want to go from tau back to z, I subtract the m and I divide by e to the s. Okay, so again, easy to apply, easy to invert. If we have, okay, so these general transformations are slow to invert. They're not amenable to both sampling and density estimation because of this. One way we can resolve this a little bit is to use something called coupling layers. The idea is to restrict, remember how at the Bayesian network, when things were too connected, we had a problem, and so we threw away connections. We're going to do the same thing here. We're going to make, instead of making this fully autoregressive, there's going to be a very limited connectivity between which variables affect which other variables, going to make things more efficient. Okay, so the coupling layers restrict the dependencies, and this allows fast inversion of the flow. The earliest version of coupling layers, like in NICE, used two groups. So we can talk about ZA and ZB, or you can think of them as Z1 and Z2. And the idea is that the first, you can think of this as this diagram with just two columns, like with a Z1 and a Z2. That's all. Okay? Well, in that case, the transformation I apply to Z1 doesn't allow me to change anything based on the conditioner. Okay, so actually what I'm going to do is I'm not even going to change Z1. I could decide to train it to change by a fixed factor if I wanted to. And then when I transform the second value, I'm going to only let it depend on the first value. Now, if I only have two variables, that's fine. But now what I'm actually going to do is I'm going to take this whole D component, so I'm going to divide it into two blocks. The first half is going to be unchanged. The second half is going to be transformed, but the transformation is going to be obtained from only the first half. Okay, so this means that our Jacobian is far less complicated than a full than it was before, but it's still going to be triangular, so we're still going to be able to do everything we wanted to do before. So in this situation, what's nice is the forward transformation was always computationally efficient, so that's not the problem. But for the reverse computation, because I'm not changing Z1, I immediately have access to it at the same time as I have access to the second part. So I can actually invert this in constant time too, because I can use these same values, which are exactly the same as X and Z, to find the conditioner values for inverting the transformer for the second part. Okay, so this couples two blocks and is constant time, but I could find lots of possible range of values in between where I'd break up all my Zs into more blocks, like 3, 5, 7, whatever. And the more blocks I use, the longer inversion is going to take, but the more flexible my transformation is going to be. Okay, so that's the trade-off between expressivity and inversion time that comes up when we use a coupling layer. Okay. So I think this is a good slide to finish. Sorry, I'm a few minutes over. And I think we are not going to get to as much of the VAE stuff as I was hoping for. But we've covered the essential concept underlying normalizing flows, which the last piece I've been showing you now is that we design our flow, typically the simplest stuff, so that our Jacobian is triangular. This allows us to effectively get the log determinant Jacobian by taking the logs of the values on the diagonal of the Jacobian, and we design our transformations so that we can efficiently implement them in one direction, and if we simplify them, then we can make the inversion more efficient. Okay, So most further research considers new flow components that give us different trade-offs between these different components. And I'll talk more about that tomorrow. So I think this is the place where we're going to wrap up. Last chance for questions before maybe Gianluca can come along and start setting up in the meantime if he wants to.